So far we have discussed about the how to measure or determine the effectiveness of a full wave rectifier. Now let's have a comparison between the half wave rectifier, a center tap full wave rectifier and a full wave bridge rectifier. Let's have the comparison between these three rectifiers. Because of if you consider the number of diodes used in the for the purpose of rectification, the half wave rectifiers requires only one diode, and the center tap full wave rectifier requires two diodes, and the bridge rectifier requires four diodes. And the need for a transformer, usually if the voltage is not that much high, this the voltage is having the comparable limits of our application, then the transformer necessity can be avoided, or can there is no need of transformer in the case of a half wave rectifier and in the case of a bridge rectifier. But for a center tap rectifier we always need a center tap transformer for the rectification purpose. And if transformer is there in the circuit, then the circuit will become heavy, or it becomes a bulky one. And now let's consider the efficiency of these three rectifiers. We have seen that for a half wave rectifier it is 40.6% efficient, and the full wave rectifier is having a efficiency of 81.2 percentage. Both center tap and bridge rectifiers having the same efficiency. And since the efficiency is determined by the output power to the input power, then another one, the quantity which determines the effectiveness of a rectifier is the ripple factor. The ripple factor for a half wave rectifier is found to be 1.21, and remember that these are all theoretical values. The actual efficiency will be less than 40.6 for a half wave rectifier, and for a center tap and bridge rectifier the maximum efficiency is 81.2%. In practical cases it will be less than 81.2 cases. This maximum means for all ideal purposes. That means the diodes are assumed to be ideal. For the case of ripple factor also, the maximum the ripple factor for a half wave rectifier is obtained to be 1.21. That means the component of AC in the rectifier output is greater than the component of DC in the case of half wave rectifier. The center tap and bridge rectifiers having the ripple factor of 0.48. And comes to the frequency, output frequency. Half wave rectifier is having the same frequency as that of the input signal, and center tap and bridge rectifiers we have seen that the output frequency is twice the input frequency. And another important factor which we should consider while using a diode for any purpose is the peak inverse voltage. So when we are using a diode for half wave rectifier, the peak inverse voltage is Vm, and for center tap and bridge rectifier, for center tap rectifier it is twice the Vm, that is twice the maximum voltage that appears across the secondary. And a bridge type rectifier will also have the peak inverse voltage as Vm. We have seen all these things. So this is the comparison between the three type of rectifiers. Now we have seen that a rectifier output contains a pulsating DC. It is not a pure DC, but in most of the electrical appliances or electronic devices which needs a pure DC or a constant voltage as the supply. So usually the rectifiers which we have discussed so far as having a pulsating output or pulsating character, that means which contains both AC component and DC component. The AC component in the rectifier output is undesirable and must be kept away from the load. This purpose, that is keeping the AC component away from the load, is fulfilled by using a particular type of circuit which we are calling it as the filter circuit. Filter means it filters the AC component and it sends only the DC component to reach the load. So filter circuit is a device which removes the AC component and allows only the DC component to reach the load. And from this diagram we can see that the filter circuit must be installed in between the rectifier output and the load resistance. So rectifier will have a pulsating DC, then we should have a filter circuit to filter out the AC component, and the pure DC has to be obtained across the load. A filter circuit is generally a combination of capacitors and inductors. So the combinations of suitable combinations of capacitor and inductor serves the purpose of filtering action or filtering. So before discussing the different filter circuits, let's have a look into what properties of this capacitor and inductor serves the filtering action. The filtering action of the capacitor and inductor actually depends on the basic electrical principles. So let's have a look into each one. The capacity, first one we have to consider the capacitive reactance. The capacitive reactance means it is the opposition offered by a capacitor to the flow of current. Usually if you consider a resistor, we call it as the opposition offered by a resistor to the flow of current is called a resistance, and usually it is pure ohmic resistances. But if you consider a capacitor in a circuit, and from the basic principles of electrical technology we can see that the capacitor offers a opposition or a resistance to the flow of current, and that is called the capacitive reactance, and the expression for capacitive reactance is given by Xc is equal to 1 by 2 pi Fc, where F is the frequency of the applied signal and C is the capacitance of the capacitor used. So for a DC, you know that if you consider the direct current, its frequency is equal to 0. So if we substitute it here for a capacitive reactance for DC is comes out to be 1 by 2 pi F in 0 into C. F is 0 for DC, so 1 by 0 is infinite, or we can say that a capacitor offers very high, ideally speaking, infinite reactance to or resistance to DC. That means a capacitor blocks the DC and it will not allow a DC to pass through it. And for an AC signal the frequency F is large, and in the case of a rectifier output the frequency of this rectifier output is twice. For a full wave rectifier it is twice the input frequency. So this F is large, and if F is large then Xc is very small. That means it offers very small reactance to the AC. That means that law means it is negligible. That means we can say that a capacitor offers negligible reactance to AC. That means a capacitor passes the AC. So these two things are very important. The capacitor blocks the DC signal, and it allows AC to pass through it without any opposition. Similarly, if you consider the circuit which contains an inductor, then according to the basic principles of electrical technology, the inductive reactance is given by XL is equal to 2 pi F into L. Inductive reactance means it is the effective opposition offered by an inductor to the flow of current. So the resistance offered by an inductor is represented by inductive reactance, and which is given by 2 pi F into L. So for again for a DC signal, frequency is equal to 0. If f is 0, then XL is equal to 0. So XL for DC, that is the inductive reactance for a DC signal is found to be 0. That means an inductor offers very low or 0 reactance to DC. Ideally speaking, it is 0, but still have a little resistances due to ohmic losses, because you know that inductances are made up of the windings of the conductors. Usually copper windings are used as the inductor, so copper will have a very small negligible resistance, so that loss will be there. But ideally speaking, an inductor offers very low or zero reactance to DC, means that an inductor passes DC. And since f is large for an AC, or there is a finite value for the frequency for an AC signal, then there is a finite value for the inductive reactance when an AC is applied across an inductor. That means we can say that an inductor offers high reactance to the alternating current. That means we can say that an inductor blocks the alternating current or AC. So here we can say that an inductor passes DC without any resistance, and it blocks alternating current. These two factors, that is the capacitor allows AC and blocks DC, and the inductor allows DC and blocks AC. These two factors makes the capacitor suitable combination of inductor and capacitor can be used to remove the AC component in the rectifier output. So the suitable combinations of inductor and capacitor can effectively remove the AC component in the rectifier output, allowing the DC component to reach the load. So these two so by using the suitable combination of inductor and capacitor, we can use different filter circuits. There are three types of generally or commonly used the filter circuits are of three types that we can discuss in the next lecture. Thank you.